Today we are going. Today we are going to continue about trees, specifically about binary search trees. You already got last lecture about binary search tree. So I will try to just focus today on the concept of recursion, because last time I was not happy with the way some functions was explained, like max depth, if you remember, because I think you did not get the concept of recursion, neither in the lab or in the lectures. So today I will explain the recursion concept and try to read the explanation about the max depth function, and then move to other examples for binary search tree functions. Okay. So first of all, the concept of recursion is simply like calling the function. If the function is calling himself, this is the basic concept of recursion. And most programming languages allow this type of calling the function inside itself. So this is the basic concept of recursion. Recursion has two properties should be met when you want to use recursion. First of all, you need to have base criteria. That means that you need to have or define a condition that breaks the loop. I mean, when you call the function inside itself, that means you may end up with an endless loop. So you need at some point of time to break this loop. So we already saw in some functions that we define like a condition: if node equal null, for example, return 0, right? You remember that?
Yes.
Yeah. So this condition breaks the loop. The next property is called progressive approach. That means in each iteration you should come closer to the solution. I mean, if you have like let's say 10 iterations, each iteration should be get closer to the solution. So you need to come closer, not further from the solution. So these are the two properties, and I think that's why we use recursion in programming. That this style of coding sometimes is more clear and simpler to implement a function or a method. I think I showed to you an example of code written in recursive and using while loop, and we already did so last lab. So when you write while loop instead of recursion, sometimes you ended up with like discussing too much cases, but in recursion it will be simpler to use recursion. Especially for data structures like trees, recursion is essential to be used. As an implementation for recursion, it's basically depend on using stacks. So whenever you call a function, inside itself you make a push to a stack. So if you have here like this diagram, you have like 3 instances of the function, or 3 calls, recursive calls. Each call will be recorded in the stack. So and if you remember, the stack concept is do you remember the concept of stack?
Yes.
First in, first out,
something first like this. First out, yes.
Actually, it's in reverse. Last in, first out. So the last entered item will be the first item to be popped from the stack. Okay. Yeah. So this is you should recall that from stack, that the last item you push, the first item you will pop from the stack.
Okay, yes.
Okay, so again, the concept is very clear. Each time you call, let's say that first instance is fn. So you and then you have a call for the same function inside it for n minus one. So first we record fn and then n minus one and lastly n minus two, for example. When we want to execute the stack, we will execute first fn minus 2, then fn minus 1, then fn.
Yes.
Okay.
Yes.
Clear?
Yes.
Okay. To give like a term analogy or a real life example, let's imagine that we are in a queue for buying something or for buying for on in a cashier, and we have we have too much people in this queue, and we want to count the people not from external view but using the people themselves. But we have two rules. Only the person can ask the person in front and behind. So you cannot ask, let's say, the person in the last of the queue. This is rule number one. And there is one question can be asked. Do you have a person behind you or not? If we want to implement this as a recursive solution, then we will make each person asking the person behind, do you have a person or not? If there is a person, you will return 1. If not, you will return 0. And once you reach to the last person, you start adding 1 to the answer. I mean, like last person in the queue will return 0, but the value that last person will return is 1 plus 0. Then the second one from the last of the queue will be add also 1, so it will be 1 plus 1 equal 2. Then the third person from the last will add also 1, and so on. So you end up with the first person. The first person will have the total summation of the people in the queue.
Yes.
Is it clear?
Yes.
Yeah. If we want to explain this as a code, simply as again, you have a question. Do you have a person behind you or no one behind of your current position? If there is no one, you will return 0. If there is,
and we add 1.
You add 1 and return the people count, and you return the people count. This is the iteration. The recursion is here with the return.
Yes.
Okay. And then add 1. So this is the code of this analogy. Now I want to return back to the max depth function we saw last session. If you remember, that was to calculate the depth of the tree. That means the longest way that connects between the root and the leaf.
Yes.
So in this case,
use left and right, then adding 1.
Yeah, exactly. So now I will explain this using the thing I already explained. Let me open. For you, I mean the size is okay.
Yes. Okay.
Yeah. Let me bring also the code. The code is clear. Okay. So let's start by drawing the stack. Let's say we have the stack here. Okay, we'll start with here is the start. Okay.
Yes.
So this is I will express by this by let's say times 0. First call will start from here, and then we go down the stack. Okay. So if we have this tree and have this code to calculate the depth, we will start by explaining line by line or code by code. First of all, we will call max depth with the root node, which is 1. So we call max depth the root. Let's say we created that the tree and we have the address of the first node, so we pass it max depth 1. So our first entry in the stack is max depth 1. This is the first entry. Now let's see inside the function. Inside the function, we first check if node equal to null, return 0. This is this node is not null, so we will pass the if condition. We'll go to this. We will create a variable called ldepth and assign to it the return value of the max depth. That means the same function, but this time with the left node. So it should be 2. Okay.
Okay.
So now the next entrance, the next entry is max depth 2. Max depth 2. Then in this point, this is a very important thing in recursion. In this point, the execution of max depth. Currently, we are discussing max depth 1, right?
Yes.
Yeah. When we reach to a call for the function itself, the control for this instance, the current instance of the function, will break and deliver the control to the next call. That means when you call max depth 2, it will go to 2. Okay?
Yes.
So at time 1, the max depth will be 2. And now we are discussing this iteration, discussing max depth 2. So again, we go to the beginning of, the next important thing that all information related to max depth 1 will be stored in the stack, and when you go back to the execution of max depth 1, you continue from the place you stopped in it. So you stopped here. So here, you stopped here in this line.
Yes.
So next time, or when you return to the execution of max depth 1, you return to here. Okay?
Okay.
Okay. So let's see the max depth 2. We enter to max depth 2, but this node is created, so it's not null. We go to else, and again we go to ldepth and call max depth for the current node, the left of the current node. That means the left of 2, which is 4. Okay?
Okay.
So again, we stop here at this point, and enter max depth 4 to the stack. Okay?
Okay.
So here, max depth
4.
4. And this is another entry. Now, for max depth, just 1 second. For max depth 4, we go now again to the first line of the
Sir,
function.
sir, what did you say? What did you say, Lester? I couldn't hear because your screen and your camera is just gone.
Yeah. So I'm telling that we are now discussing the execution of max depth 4.
Okay.
Okay, so we are again going to the first line of the function, but now with execution of node 4, this node. So is this node is null? No, it's not null. 4 is created. So we go again to the else. Now we call ldepth, and to the left of the current node, that means to the left of 4. What is the left of 4?
Null.
Exactly. So now we go.
4 return 0.
Exactly, but let's do it step by step.
Sorry, your voice is gone.
Another entry. So now we will discuss max depth for null. So let's go to the beginning of the function. Okay.
Yes.
Yeah. So we will check the value of node, and actually we are passing value null. So node is actually 0. Okay.
Okay.
But the return 0 will be for here. So here we return 0. Okay.
Okay.
But max depth 4, where was the last line executed?
I didn't understand.
I mean, in max depth 4, which part of the code we stopped executing?
Left, so.
ldepth.
Oh. Yeah, in the left, the last one was left.
Yeah. Okay, but I mean, which line of the code we stopped executing for max depth 4?
Okay. Fourth.
Sorry?
Fourth line?
No. I mean, this function has lines of code, right?
Yes.
This is line number 1, line number 2, 3, 4, 5. I mean, which line of code we stopped executing to go for max depth null? This line.
Yes.
We executed this line and went to max depth null, which is the left of 4. Right?
Yes.
Yeah. So this return will return to max depth 4 and will be returned to the ldepth value. So this value will be now equal to 0. Okay?
Yes.
Yeah. Okay. So the execution, again, as I told you, the execution, whenever you have a call for the function inside itself, the execution will stop and go for the next iteration. So at this point, by calling the none, we have a return, so we stop execution of this entry. So this entry is already executed. So we go to the and again, if you remember, I told you the stack last in, first out. So the last thing in the stack will be executed. The next item will be max depth 4, right? And the return value is 0 from the max depth 1. So ldepth equal to 0. Okay? And the execution now under the control of max depth 4. So we go to the next line for the max depth 4, which is r depth equal to max depth again, but for the right node.
It's again.
Yeah, so it just for to be clear, we will write again the max depth null, but this time max depth null, but for the again the right of 4, not left of 4.
Yes.
I will write max depth 4 to the right just to be clear, because we will have too much calling of max depth now, okay?
Okay.
So now the execution of max depth 4 will be interrupted again, and we enter a new entry for the stack, which is max depth 4 to the right of the 4, okay? So again, the last input, the first output in the stack, so we will execute max depth right of the 4. And right of the 4 is null, so again this will return 0. Okay?
Oh, okay, yes.
Yeah. This time return 0 will be for which line? And we stopped executing the right of the 4. We return to the max depth 4. So on which line will be the return?
Right depth line.
Exactly. For now,
Yes.
our depth is executed and have the return value, which is also 0. So now we have in this line, I mean the L depth is 0 and the right depth is 0 also. So we continue execution. Now we check the values by this condition. If L depth greater than right depth, we execute this, else we execute this. So which line will be executed?
Else return.
Else return, exactly, because 0 is equal to 0. So yes. Now we will return from here. We will return the value r depth plus 1, and r depth is 0, so we will return 1. Okay?
Yes. Okay.
Here the return now will be from max depth 4. It will return to max depth 2. Okay? And return by value 1. Max depth 2, at which line we stopped executing?
Else return.
Sorry?
Last time we did else return.
No. The else return was for max depth 4.
Mm-hmm.
I mean for max depth 2, which line we stopped executing?
L depth.
We stopped at L depth, so L depth now has a return value from max depth 4 and return with 1. So L depth now equal to 1. Okay?
Okay.
Now we go to the next line, R depth. R depth, now we have another recursive call for max depth, but this time for the right of 2. So we will have a new entry with right of 2. Okay?
Okay.
But the right of 2 is
null,
so it will return 0.
0, yes.
So it will return 0 for max depth 2. So the right depth, R depth, is equal to 0. Okay?
Okay.
And this one is executed. So now we have the value of L depth and R depth. So which return will be executed?
Answer.
I mean, which return will be executed according to this case?
Answer.
No, not the S return. It will be the first one because L depth is 1 and R depth is 0 and L depth is bigger.
Okay.
Okay, so it will return L depth, which is 1 plus 1. That means it will return 2. Yep.
Yes.
And now the return will be for which instance of the function?
I didn't understand.
I mean, now we finished executing max depth 2, right?
Yes.
So now to which instance or which entry from the stack will be
Max
returned?
depth 1.
Exactly. And the return will be 2.
Yes.
Okay. So now we return back to the root. 1 is the root. So and again, at which line we stopped executing for the root? The L depth.
Yes, L depth.
Yeah, because all of them stopped for L depth and then R depth and then continues the execution. So L depth now equal to 2. Okay.
Yes.
Now we call the R depth
R depth. Yes.
the right of 1, which is the 3.
3. Yes.
Yeah. So now we will have a new.
Someone.
It will stop executing max depth 1, and we will execute max depth 3. For max depth 3, we will start from the beginning. It's not null.
Yes,
We go to the left of 3. It will be null.
Yes.
Okay, so it will return 0.
Yes.
I will just pass quickly for this information.
Yes.
It will return 0, and the L depth, right depth also
Is null.
Also null. It will return 0
Yes.
also. So the else return will be returned, and will
Plus
return
1.
value 0 plus 1. Okay, so it will return 1. So max depth will return to the max depth 1 with value 1.
Yes. So right depth is 2, and left is 2, and right is 1. So in the end, we will calculate again with if, and then we will add 1, and the answer is 3, I guess.
The total return will be 3.
Yes.
So is it clear or you
Yes,
want me
please.
to?
Thank you.
Yeah. So I think by now it's very clear how recursion is working.
Yes.
Right?
Yes.
Yeah. It's very important to understand recursion because you will see that all the functions inside the binary search tree is implemented with the recursion. If you cannot do this analysis, you cannot understand how the code is working. Okay. So if you remember when we executed this function with this tree, the value was 3. So the answer is identical to the analysis. So let's continue with the slides. Okay, so the next slides, I'm just repeating what I explained with the whiteboard or blackboard. I just did the same thing. I explained to you how we filled the stack with the calls the recursive max-diff. So it's the same steps we did now together. And the result is equal to 3.
Yes.
So let's go now to another thing we use for binary search tree called the traversal algorithms. I think you already get in lectures the algorithms, the post order, in order, and pre-order, right?
Yes.
Yeah. So just to give you a basic idea of the any traversal algorithm, the basic thing about this algorithm is to go through all the nodes. So you need to visit all nodes of your tree. I mean, all algorithms has one objective, which is visiting all nodes. Okay?
Okay, yes.
Yeah. So we will have this basic tree, and we will again we will execute the code of each algorithm on this tree in a recursive style. Okay. Okay. So let's start with this tree. Let me bring the code and the tree to our program. This is the post order. This is the post order algorithm. So let's start. Just for this algorithm, I will draw again the stack to understand. But for the other two algorithms, we will explain it like in our mind. Okay.
Okay.
Okay. So let's start. I will draw the stack first. And the stack starts with the first line. The first line is the first entry. Okay.
Yes. Okay.
So let's start. We will call this function print post order. It will visit all nodes and print them. So that's why it's called print post order. So we will call it with the root node. So we will call print post order for 25.
Yes.
Just for speed, I will call it PPO.
Okay.
First entry is PPO 25. Let's see what will happen when we call PPO 25. It will check, it's not null, so it will go for this line, print post order for the left. Okay? And left is 15, so it will stop executing and go to PPO 15.
Yes. Then PPO 10.
BBO 10, yeah. Now what is
And then
the
PPO false.
exact? Now,
Well, there is no note at 4, so he will return it.
to which one return?
10, PPO
Exactly. And return with what?
10. PPO 20. I mean, if it will be first check left.
Now 4 is done. 4 is done. So sorry, not for the BBO left of 4 is done. So it will return to BBO 4 the 0. So let's write it just.
Allahu Akbar.
BBO 4 to the left will return 0 to BB4.
Yes.
Yeah. So so return 0 to BBO4, which was in this line. Okay. So this line has no any like thing, so it will return 0 here. We go to the right. So yeah. So the right of 4 is what? Also null. So also this line will not have any thing to print. Now we go and say cout node data, and we are in 4. So it will print for us 4. Right?
Yes.
So this is the console. So we will have now we will print 4, and BBO4 is finished executing. So it will return to the 10.
Yes.
Okay. So BBO10 stopped at this point. Now it will go to the right. The right of 10 is what? 12. Okay, now 12 has the left and right are null, so it will return 0 by 0. And then it will, we will again now, so it will execute this line of code, which means printing 12. Okay?
Yes.
So 12 was the last execution. If you imagine what is inside the stack, so we will return now to 10. 10 not finished executing. The last line was 10 right to the 10. So it will print itself and return.
Yes, 10.
Okay, and this is another note. You can return from the function by explicitly saying return, or when you reach to the end of the function. So here you don't see return, right?
Yes.
Yeah, explicitly it will return to the next function.
Yes, sir.
So now we will execute 15. Yeah. So 15 stopped at left. It will now go to the right.
Right, go to the right. Yes.
Yeah. So it will
22.
now. Yeah, 22. What will happen here?
And then we will check the left one, and it will be 18.
18. So
then yes. Okay.
Yeah. So 18 has null from the left and the right. So we'll simply execute 18, right?
Yes.
Yeah. And the execution before 18 was 22, and it was in the left. So it will go to the right, which is 24.
24, yes.
Yeah, and 24 again, left and right are null, so it will print itself
Yes.
and return to 22.
Yes.
Right? So now 22 has nothing to do except printing itself, and go back to 15.
Yes.
Clear?
Yes, clear.
Yeah. So it's 22. And
Then
15
we will
now.
go to again 25.
15 now is finished. We will
Yes.
go back to the root.
25.
Now the root stopped at left. It will go and check the right, which is 15.
Yes, 15, yes.
50, sorry. 50. 50 will check what? The left,
Left, 35.
which is 35. And then 35 will
Then
check what?
check left, 31.
31. So 31 has none to the left
No
and the
noise,
right.
yes. We
Yeah,
will
so
print it.
it will
Then
go
we
to
will
the
go to
35.
the right, 44.
44.
Then
So
there is no road, so we will print it.
exactly.
Then we will return 35.
So
We will
now
print 35 because
35.
there is no note.
And then
Then
we
we will go back to 50.
50. It will go to 70. And 70 go to
Yes.
66.
Yes. There is no note in 60, so we will print 66.
And then
We will return 70 and 90. Then there is no note to 90, so we will print 90.
very
Then
good.
there is no note, so we will return 70. Then we will return 50, then we'll return 25.
Exactly. Very good. Very good. Okay. So this is the order of nodes visit. If we wanted to, let's say, like these tricks will help you in the exam, or like memorizing the algorithm. So you will have like 3 or 4 algorithms for traversing. So it's hard each time to do this in your mind, or you have like limited time to answer the question. So you need to find a way to memorize how the traverse work, this algorithm work. So simply you draw a line of how this function visit the nodes. So let's see what I mean. If we imagine this line is how the order of printing. So 4 is printed first time. Sorry. 4, and then 12, then back to 10, then go to 18, then 24, then sorry. So 18, then 24, then 22, then 31, then 44, then 35, then 66, then 90, then 70, we missed 7, 15, 7. We missed 15 here. 15 should be printed. We did not print it in the console, but it should be here after 10. Oh, okay. We missed and write it as 18. It should be first 15, then 18. Okay. How come?
Oh, sorry, my microphone was muted. Yes.
Yeah. I mean, we missed printing the 15. So we simply after 10 there was 15. Here from the list was 15. So we just missed here the 15. 15 should be here. Okay.
Yes. Okay, sir.
Yeah. So let me just erase the thing. So again, let's imagine how this algorithm traverses. So you can answer the question very fast if you do so. 4, and then 10, and then 15, and then 18, 24, 22, 31, 44. Sorry. Like this. Then 18, 24, 22.
Yes.
Stuff. 4, 12,
Yes.
10,
Yes.
15, 18, 24, 22, and then 31, 44, 35. Then,
Sir,
yeah, so we missed the 35. It's
Sir?
just, yeah.
Aren't we has to go, 4, 12, 10, and then
Yeah.
we have to go 22, right?
Actually, forget about printing on this blackboard. Let
Okay,
me show
I
you the
got
answer.
I got the
Yeah,
point.
the
I
idea,
got the point.
yeah. So just like this. Okay, so you start by here, 12, 10, 18, like this. So you need to understand that you start by like the last leaf on the left, and then you go right, and then to the upper node. Then you go and finish this side, and then go to the one. In here, I think I drew it. No. Actually, it was not. It was not fault because the root is the last one executed.
Yes.
If you remember, the root here was last one, 25.
Okay.
So just to solve it quickly, you should start by the first leaf on the left and ends with the root here, and you should follow the root like this. Okay, like a maze.
Okay.
Okay. So this is about post order. Okay.
Okay.
The in order we can do it like quickly, very quickly. I will make a snapshot for it and go again. But this time we will analyze it with our brain without writing the stuff. Okay.
Okay.
Let's see if we can do this.
Can I try to do it?
Sorry.
Can I try to do it?
Yeah, sure.
So we can.
Let me
define
just just 1 second. Let me enlarge it. Okay. Yeah, you can start.
Okay. First, I will start with 25, and then go 15, then go 10, then 4.
Wait.
Then I will print
No.
4.
You should see now the change now that the right. I mean the print of the node is not the last part. It's between the left and the right. Okay.
Yes.
So 25. It's correct. You go to the left, but now after you go to the left. Oh, okay. No, I'm sorry. Yeah. Continue. Yeah. You go to the left of 15.
Then I go to the 4.
Yeah. Exactly.
Then I will print the 4.
You print the 4.
Yes.
Yeah, just let us write it.
Then
Now you
I
go
will
back.
Then I will go back to 10. Then
10
there is
was
no
at
I will
left.
print. Yes.
Yeah. So you should.
So I will print 15.
No, 10. You stop at 10.
Oh,
So
okay.
you should
Then I
print 10.
Yes, I will print 10.
Yeah. Then
And 12.
do what?
12.
You call print in order for the 12. So there is no left. So and no
Yes,
right.
no left.
Exactly. So
Then I will go back.
No, now you go back to the 15.
No, I will print 15.
Exactly.
Then I will go to 22 because we use 10.
You print.
Then-
You go to the right. Yeah. 22.
Yes, then I will print 18 because there is no notes.
Mm-hmm.
I will go back and print 22.
You go back to the 22 and print
I will
it.
print, yes. Then I will print 24. And I return
To the
it Yes, and I will go back to 25.
25 exactly, and
I will
print
print
it
25. Then I will go to the left
to the
and
right.
to the right, sorry, to the right.
50.
There is 50, and I will go left, and then left 31. I will print 31, and then print 35. Then 44. Then I will return 50. I will print 50. I mean, then I will go back to 66. Then I will print 70. Then 90.
90, and this way we here just see like started by the uh, the left leaf at the most
Yes,
left leaf, and then ended with the most right leaf here, like this
yes.
way. Okay, that's the point I just wanted to tell you. Like you can memorize how the algorithm execute. Like if you can memorize this, the way of executing. For example, for in order is more easy to like to just memorize how it will go like this. Okay.
Yes, okay.
Or you simply do it like in your mind, like what you did right now. Let's do the pre-order the same way.
Yes.
So again, let's do it using our mind.
First of all, we will start with 25 because head. And there is no head of 25, so we will print 25. Then we will go left, 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 and we will print 4.
But no, you should now take it. Now each left
okay.
you print
Yeah.
it. So
I
it's
guess 25.
15, 10, and 4.
Yeah.
Okay.
Yes.
Now you go back. 4 is finished. So there is no left and right. It will go to the 10. Right.
That's right.
Now the right of 10. So you print 12.
Yes. Then I will go back. I will print 22.
You print 22 and you go to the left.
Then 18.
18.
Then 24.
24, exactly. Now you go back to the 25,
Yes, go back
to the right.
I will print 50.
50.
Then 35.
35, 31.
Then, yes. Then I will print 44.
Back,
Okay, here I print 40.
you print 70.
No, 66. No,
70.
yes, 70.
Yeah. Because
Then
the
66.
first part is also
Yes.
all the time printing. So then 66, as you said.
Then
Then 90. So this is the solution. Good job. Let's see how the like this line will go like this way. Okay. So we started with the root and ended with the most left leaf on the right. Actually, it's important to memorize this because you can. Let's say you have a question. The exam. Let's say if I ask you, if I gave you a tree without drawing it, and I told you that these the nodes are the following. Let's say like let's just give you these numbers, okay? And I told you that for these numbers without seeing the tree, okay?
okay.
And asked you is this order post order or pre-order or in order? Your answer, can you answer this question?
Okay.
Yeah, can you try to answer? how you can check if the sequence is in order or pre-order or post-order?
With the order.
Very quickly. If you just check if it start with if it's end,
yes.
for example, with the root, you know that this most probably will be the post order. If it's not ended with the root, it will be something else. You got it?
Mm-hmm.
So this is this is a trick how you can find the answer or make sure if this answer you can know quickly if this is post order or something else. Whenever you see the last node in the order is not the root, this order is something else than post order. Okay?
Okay, yes, I understand.
Okay. So by doing so, we explained the three algorithms. I'm just this is an example of like what I'm saying right now. You have the sequence of the pre-order, and they asking you to print to draw the tree. Okay.
Okay.
So let's try to solve it by ourselves. Let's see how we will solve it. So first of all, let's understand the question. They said given a PST in pre-order, so let's go and get the pre-order algorithm first.
Yeah.
This is the pre-order.
Yes.
And let me bring it with the draw.
Mm-hmm. So the first set is 30. 13.
Yeah, you can get the remark here that the first thing is the root function.
Yes, no. Head of that. And left and right.
First thing we can say, like as you said, as it's pre-order, so 13 is the first. Let me choose it. 13 is the first node. Now it's
Yes,
saying
and the left one is 5.
yeah, but let me draw the solution as you are going to tell me. Then discuss what you want to do.
5.
5. Okay.
Yes.
After 5.
Then 3 to the left.
Mm-hmm.
Then 2 left again.
Mm-hmm. Okay. What about 11?
Then 11 is bigger than left. So we'll write 2 right, I guess.
It's not bigger than 13. So bigger to the right of 2 or what?
Oh no.
It will be like if you remember in BST, you should be in the same level. I mean, 11 is bigger than 2, and 11 bigger than 3, and bigger than 5. But when you want to insert it, it should be like
yes, we will
right to the biggest one between this
right,
sequence. Yes. Yeah, so it's right of 5. Yes. Now the next one, let's just check this. Now we have 7. So 7, where you think we will put it?
Left to the 11.
Left to the 11, right?
Yes.
Why not here? Let's say.
Because we finished it. We finished here.
Exactly.
And we had the right notes.
Exactly.
Because we can't write the left.
Good job. So now 19.
19 is bigger than 12.
No.
So we will write.
Yeah, now you should see now 19. It will be like this case. Let's say this case you finished the left branch. 19 is bigger than 13. So
And we
you
will
do
write right.
here. Okay.
Yes.
So now 19.
Then
22 is
we will write again 2.
22.
Because 22 is again.
Okay. Not to the right, to the left of 19.
Okay.
To the right, not to the left. Just right, because it's bigger than. Okay.
Yes. Okay.
Okay. This way you solve it. Let's just to make sure this is correct. Thirteen, 5, 3, 11.
So I can't hear your voice.
Or we did a mistake now by putting 7 after 11. Let's check the pre-order. Algorithm again. The pre-order says left and right. Left and right. It's print, left and right. So we print the two. Print left and right. So actually 11 and 7. Yeah. This one is not correct. It should be like as we solve it now. It should be 7 here, not here. I will correct it now.
Okay.
If it was like after 3, it should be like this. But according to the sequence, it's after 11. Okay.
Okay. Yes. I mean, it's good. Yes, of course. It's definitely wrong because he prints first 11.
Yeah, if it was print after 3, that means if it's...
Then maybe
right.
Yes.
So you have two options, but the option will be like you determine according to the order you have. Okay?
Okay.
So I mean like a BST, it's correct to have 7 here in this branch or after 3, like here to the right of the 3. But according to the order, 7 should be here. Okay?
Okay.
Yeah. Now they asking now the next part. Is it the same of the order given in post order? Is it the same of this tree? So let's go back to the post order.
Yes. Left, right, and no.
Yeah, just let's solve it again and make a basic check first with the remark, and then see if it's the same or not. Let's clear this and clear this.
So can we give a break for 2 minutes so I can drink water?
Yeah, sure. Just to check if the same, is it the same tree? So in post order, first thing to check if the last node in the sequence is the root. So it's actually it is 13. The first in pre-order is the end of the post order, so it's 13. So let's start drawing the tree. 13. Remember, in post order you go to the left and right and then print. So 13 Yeah. So when we say two means it's the last node. So when we have 2, that means we have here the last node is 2.
Yes.
Before it is 3. Before it is 5. And
Yes.
7 is
Right.
right of it. It's left, right, and print. So
But first we print the 11 in the first pre-order.
yeah. Here 7 and then 11. Sorry. Here is should be 11 then 7.
Yes.
Yeah, exactly. Now we go to the right branch, which is
23.
Now after we finished here, now we go to the right of 13. I mean 7 and 11 was the last part of this subtree. So now we go to the right of the root node here to the right. After we go to the right, we go to the left of the node, the next node.
Yes.
So it's left 13 will be the here, like something here, and then then 30 is the last left here. 90 is 90, but it will be like here, and then the 23. Let me just erase it because it's not.
But sorry, we already print 12 in
Yeah.
the head notes.
Let me repeat again. Now we reach to the. Actually, 13 is not printed yet, but we know that 13 is the.
Yeah.
Okay, I understand you. Yeah. 13 is here, the row. So let's just check them. 2 is printed. 3, 5, 7, 11.
11.
Yeah.
Then
Now
there's 2.
13. Now we have two things to do. 23 and
Yes.
19. So 23 is the most left in this branch. So it's 23. Now the 80 is here. Okay.
Okay.
So it's identical, I think, right?
Yes.
Go back to the
But it's
slides.
not right because in the pre-order 19 and 23's direction was like that.
Yeah, it's the same. It's 23 and 19.
Oh yes. Okay.
13 here, sorry, 23. 19 and 23. So it's
Okay.
identical. If you compare it, it's identical. So the answer is yes. The answer is it's both are the same. Belongs to the same tree. I'm just thinking about a scenario. Can we, like, if we have this order, can we say 23 and 19? No. There is no way. I was thinking of not writing like this, like saying 23 first and then 19. But this is not allowed. You should start with the the smaller one here. It should be okay.
Yes.
Yeah. So the answer is just like a small assignment in the same way of what we did to solve the question. I want you to solve this question, but you have a pre-order and in order, not like here. It was pre-order and post-order.
Draw it, right?
Yeah, like you draw it and check if it belongs to the same tree or not.
Oh, no coding this time.
Sorry, no code. Yeah, just print it, like draw it like something like this.
Yes. Okay, I understand.
Yeah. I want to discuss with you, if you remember, if you remember, we discussed the marks of this course. we said we will have like final project. We'll have a presentation, which is a presentation about a project you will do. Okay, and a report. This project will be for the Abdul Hafiz Hojam part and for the lab also. So you will have a project. I found it's better to define a topic for you. So I selected for you a practical project, so you can see in reality how you will use what you are already learning to solve a real problem.
Yes.
And this, by the way, this is like a thing that you will see if you want to go for later for machine learning or deep learning, something like this. You will see too much about trees and algorithms. So it's very good to have such a project. And the concept is easy. I will explain to you what you should do. You will have something called dataset. Dataset means it's simply a data. It's a collection of data, certain data. So we call this as a dataset. In this project, you have a dataset or collection of data extracted from a website called Goodreads, if you know it. You know it?
Yes.
A website for reviewing books. You read a book and you post your review on it. Did you saw it before?
No.
Okay, this is a very famous website. Millions of people make a profile for themselves, and just every time they finish reading a book, they post a review about it. So you can see any book and or open for any book and read the review from other people. So you can take an opinion about the quality of the book or what this book is about. Okay, so this is the topic of this website. The dataset is extracted from this website. It simply contains, it's already open here, I think. Actually, it's provided in this link. You just create this website called Kaggle. It's a very famous website for machine learning and deep learning. It's almost about like what's called. They make challenges related to machine learning and post like data sets. So one of them is about Goodreads. So you just create an account and download the dataset. It's simply a file, an XML file.
Yes.
This one. It's simply like this. You have like an XML file. Inside it you have a book ID, just an ordered increasing numbers, and the title, the number of the name of the author, and some information about the book itself. Okay. So like Harry Potter, what the name of the author, the ISBN, like an international serial number for the book, rating, number of reviews, number of pages, the language of the book. So information about the book. And it's not a big data set. It's like around thousands, like 11,000 or something. So it's not a big data set. So your job divided with multiple tasks. The first task is to get the data set and read it from the C++ code and extract the data, some data from the file. You simply read the file and extract the author name and book titles. Simply just, I want from you to print the author's names inside the iteration and the name of the books. Okay.
Okay.
Okay. and this will have 20% of the project mark. Then the next step is to link what you already learned. So we will use the concept of BST, binary search tree, for the names of authors, and another BST for the name of books. You should build a tree for them. The next one, you will use the BST to do a search for a query. I mean, now you have a tree. The tree will be something like, let me show you.
Am I going to build a tree for author?
For author's name, and for the book names.
All the book.
All the books, yes, and all the authors. Let me just show you. The BST can be numbers like what we saw, and can be names like this. And that's the same concept. I mean, alphabet, in the English alphabet, you have an order. In any alphabet, you have order. So A is the first letter, then B, then C, right? So the same, like in numbers, you also order it with like bigger and smaller. And here also do the same. You order with the order of the alphabet. And you may also have like trees, binary trees with letters, not a string. We will discuss this as a next step. I want from you do it step by step, just to make it easier.
I mean, as I understand, there's hundreds of others. So how am I going to build a tree? Like, I will going to.
We will discuss this. Yeah, I understand too. Actually, you will not use like something like this. You will do it with alphabet. Let me with the charts. Let me see if we will have something. Yeah, something like this. Look. Just to give you an idea, we will discuss more, but you will have like something like organized like this. So let's say the name of the author is George, let's say. So your tree will George and Jordan and what else? You have like a common part between different names. George and Jordan, both of them start with G and then O, then R, right?
Yes.
Yeah, so the tree will be ordered like, we'll start with J, then go with O, then go with R, and then the last part will be the thing that distinguish between Jordan and George. The D in Jordan will distinguish the G in George. Okay? So it will be organized something like this. We will discuss more next session, but I'm just like giving you a hint or insight of how the tree will be look like. Okay. So using the tree, you can search like the George and Jordan. You start with J and go with O, and then you find that you have two authors. Let's say start with G and O, then you have two authors like this. So simply when you do search, let's say you can't remember the name, so you just pass GO to your search tree, and it will return for you Jordan and George. Let's say, okay. Let's say Jordan also written with G. It's J or G. Let's say it's G. The last part is just so now you have a binary search tree for authors' names and another one for book titles. The last part is using them to fetch the names of books according to a query. So you just enter like introduction. So all the books start with the introduction string will be returned for you. And the same for the author's name. Okay?
Okay.
and beside each task is the percentage of it in the project. And last thing, I will give you extra marks if you have a good design for your code and documenting the code, like adding notes describing the important thing in your code. And if possible, I'm not requesting, if possible and you have time and you want to learn something, you can build a simple GUI for it. In any way you want, And if we have time, I may help you in building a GUI for it. If we don't have time, I will not you will not lose any mark. It's something good to have, but you are not requested to do. If you do it, it's okay. If you're not, you will not lose something. But I will must look for the good design for the code and the documentation. Okay. For next week, just because I think we have only we are now 19. We have like 4 weeks, so you have 4 weeks to finish the project. So I will follow up with you week by week. So next week I want you to read the dataset I showed to you from the C++ and return for me the names of books and authors in the dataset. Okay. And to help you more, it's not you will have too much like options in C++ to read from CSV. So I helped you and put you a code you can use to read from a file and fetch from it the data. But I want you to you should know that this code here, you know the CSV files, how it's organized.
Yes, kind of, yes.
Yeah, it's a TXT file, but the data is separated with commas. With comma, right? Okay. So you have like data 1, comma, data 2, comma, data 3, and so on. So in this code, you have like you have 1, 2, 3. You have four data. I mean, you have 4 commas and 4 columns. 4 columns. In this file, you have not 4. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you just need to change this line of code, and instead of having 4 columns, you should have 11 columns. Okay.
Okay.
Yeah, so you need to make the change of this code. So just make the changes of the code, run it.
I will change the code for the next week.
And prepare it for the next week. Okay?
Okay.
So, and next week I will check with you your code and explain to you how you're going to build the binary search tree for such program.
Okay.
Okay. Last thing, also to help you, to give you extra marks, I will do a final quiz for we did not make any quiz for the lab, so I decided to make one small quiz, light quiz. It will not require from you to study all the codes. Just you need to go through the slides, make sure you understand the concepts, and it will be multiple choice for 30 minutes only. I will not ask you too much of things, and I will give 20% of the total lab marks. Okay, you don't need to memorize the codes to be multiple choice, but the most important thing, I want to see that you understand the concepts. Like today, I was happy that you could solve traversal algorithms by yourself. It was good. So I just want you to be understanding what you are taking in this lab. Okay?
Okay.
Yeah. And this one will be 8th December. I think the session before the last one. Yeah. Okay.
Okay, so
Um, can you share with me the slides?
okay, of course.
You can do it very quickly. I mean, just
Yes. There is only 5 slides.
okay. Let's see. I will stop
Yes,
sharing,
or
or you start.
4 text and 1 code.
Okay. Is it okay to post the recording? I can cut the recording if you don't want for your part. Yeah.
No, it's okay. It's
Yeah.
okay.
Okay.
Can you show? Can you see it, sir?
Yeah.
So can I? Sorry. Can I start?
Yeah. Please.
Okay. So topic is circular buffer. There is only one few sentences for the telling what is circular buffer. Circular buffer is mostly used for embedded systems. If the CPU memory is limited or you want to keep the previous data, the circular buffer will come in handy. I mean, we are using this like there is a circle, but it's not circle at all. It's in our mind, and if we want to use the data after the works, we will use circular buffer, and it's good for embedded systems. For example, after receiving the values, you receive functions to circular buffer. You can process them elsewhere. As I said, we will keep the data and we can process them elsewhere. We can keep it and we can do it for next job.
Okay. Just give you one note. You are correct. But
Okay.
just to make it more clear, why it's important in embedded system, as you said, because you have limited memory. So sometimes your processing of data is slower than the receive rate of data. So if you are, let's say, processing at the speed of 1 megahertz and the received rate of data is, let's say, 2 or 3 megahertz. So you need something slowing down the rate of your data. That's why you put the circular buffer. That means you are processing and at the same time you're accepting the data. So you're not missing any data. So you are not blocking receiving, you are receiving and at the same time you are processing. That's why it's important for the system to keep it in real time. So
Yes, and we can add new things every time to this buffer.
Okay, yeah, please continue.
And there's 2 things: producer and consumer. Producers, it saves the characters or string received from the UART in a circular buffer via a queue. What it does is to store the received data in a certain place for you. So producer is saving the data for us to use it elsewhere, and consumer is basically using the data to what we wish for. Consumer is the process of taking this data from the circular buffer queue, processing or consuming it and producing a certain thing. Of course, it depends on what you are going to use and what you want to do with that data. So the data it's up to you. We can use it everywhere. We will save it with producer and we are using it with consumer. That's the basic thing of these two. And there's 3 applications. I mean, there's more applications, but I will tell 3 of them. For the memory management, unused memory locations. In the case of ordinary queues can be utilized in circular queues. So we can use the unused memory location in the queue, so we can use again. And there's a traffic light. Their system is the computer control traffic system. Circular queues are used to switch on the traffic lights one by one repeatedly as per the time set. So there is like a loop in the traffic system. So it saves data red and light, and it shows us when time comes. And CPU scheduling. Operating systems often maintain a queue of processes that are ready to execute or that are waiting for a particular event to occur. So in CPU is important too, because we are using this for embedded systems, so we will change the data and use it for CPU scheduling.
Can you explain to me more about the memory management? I mean, traffic task and CPU scheduling is clear, but for memory management.
Memory management, there is a memory in our device, computers, etc. And we are, how can I explain? There's we are not using the every memory locations in our memory, so we can utilize it in circular, I guess. I mean, I don't know if I tell this true, but
You mean like you allocate a space in the memory without any interruption with the spaces?
yeah, I mean the unused memories.
Yeah, I mean you don't have like what's called fragmentation. The locations are in sequence.
Yes.
But this is I think it's not related to circular buffer because I think the handling of memory management is not an application of the circular buffer. Actually, if you have the resource where you can pass it to me if you have the like
Okay.
where you no later not now.
Yeah, okay. I will.
Yeah. Okay. Yeah, please continue.
Okay, sorry. Okay, sorry for that.
By the way,
So-
continue and just I will share the notes later with you. Okay.
Okay, so the implementation. So I couldn't find a decent code. I mean, there's always another code for circular buffer, but and somewhere I could understand either, but I will try to explain. So we will call a function which for the circular buffer, so we can create the buffer. So there is a notes in here for the explanation, but I will read it. We will call buffer data buffer, and for the end of the data buffer, we will use buffer end. Capacity, maximum number of items in the buffer. Count, number of items in the buffer. Size, we will look this for Z, and size of each item in the buffer. Head points to the head, and tail points to the tail. And we will use.
Can you tell me what the usage of head and tail?
Sorry?
Practically, I want you to explain to me what head and tail are really used in circular buffer.
For the data, I mean, we are starting with heads, and then finish with tails.
Okay, but when you insert a data for a queue, circular queue, what will change, the head or tail?
Oh no! First, we will go for head. Data will go for head. Then tail.
Okay, so let's say we started. Let me ask you. In the first, without entering any data, the head and tail will be what values they have.
Sorry, sir.
I mean, before the circular is empty now. The circular buffer is empty. So the head and tail should have like pointing in which way? Are they equal? Or in the same place, pointing to the same place, to the same.
No, it points to head points to the first data.
And tail.
Tail's last data.
But it's empty.
Yes.
So they should be pointing to the same place. Head and tail in the beginning should be head pointing to the same. Now we entered, let's say, 3 items. Head will be pointing to where?
To
To the first item or to the last item?
First.
Okay, and the tail?
Last.
Okay. Let's say now we make a read. You have here like Bob. Let's say you called Bob for one time. So out of 3 items, you are returning how much? Returning 1. Right? So after you calling read, the tail will be pointing to where? After calling read for one time.
So I could hear clearly.
Yeah, I'm saying like you have now 3 items in the circular box, okay? And you made a read, one read. So this one read returned for you one item. The one last item, the last item. Now you have 2 items. So the head will be pointing to where currently?
The 1.
Okay, to the first item.
Yes.
And the tail will be pointing to which item?
3.
No, 3 is already you already read it, so it's not now it should be the second item. I mean
yes.
I mean like
yes.
Okay. It's like a clock. So you have two arrows. So the read is the tail is increasing, and depending on how you know if there is data or not in the circular buffer.
For checking with if.
Okay, but checking what?
Sorry.
Checking the difference between the tail and head. If tail and head are not the same, that means you have data. If tail position is greater than head, that means there is data. That's why you are increasing the tail, so you will have a difference between the values or the pointer address between the head and tail. The pointer address with tail will be much larger from the head. That's how you know there is a data. The other question, how you know there is no data now? It's zero. There's zero data inside.
We will use count.
Okay, in this code you have count, but as a concept of data structure, circular buffer data structure. How you can use head and tail to know that there is no data. They will be equal. Whenever it's equal, that means the circular buffer is empty. So you did all the needed read operations, making the circular buffer empty.
Yes.
Okay. Let me scan the code and see if there is something I want to ask you about. In the init, what you are doing briefly? What is done in it?
Which where?
Init cb underscore init.
First, I will initialize circular buffer CP.
I just want you to give me an overall idea. I don't want you to read line by line. Just tell me what this function is doing.
Okay, so I will check the errors for if equals not.
Okay.
Sorry.
Let me ask you how you use cb underscore init. I mean, let's say without the details of these lines, how you call this function. You have 2 arguments. How you use it? Have 3 arguments. Sorry. How you use it? I mean, this is the implementation, but how you use this implementation?
Sorry. I will first avoid CPinit and this, and I will write the capacity and the size of the buffer.
Mm-hmm.
Is it correct?
You are explaining to me.
Okay, I will
So
write
size
capacity and
S is going to do what? The SZ is the size of your circular buffer. So you're doing malloc is doing what here? Malloc.
is
The first line.
Yes, calculate size.
Malloc was not for calculating size. Malloc was for allocating, dynamic allocation. If you remember, we took malloc and free.
Okay. Yes.
Yeah, so malloc is for dynamic allocation. So in this code, you are telling the user that you have the option to specify the size of your circular buffer with the SZ size.
Yes.
Okay, and you have the free and pop. Free is for deleting,
Yes.
pushback for write, and pop for read. Okay,
Yes.
I just want to. I will not get this presentation with too much marks. I just want to give you advices. First of all, the good thing that your presentation does not have too much words inside. Like too much people just copy and paste too much text and like tell the listener to just read or read the line by line text. As a listener, I don't expect from you to read for me the text in the presentation because I know to read. If I want to read, I will read the tutorial, not the presentation. So I expect from the speaker to explain by his own words during the presentation the outlines found in your slides. So it's good that you did not put too much lines or text in your slides. You tried to explain in your own words. That's good. But sometimes you try to only read the lines. So reading only the lines from this presentation that has impact for the listener. I will say in myself that the reader or the presenter has not too much knowledge about what he's presenting. But when you are trying to express with your own words, that means you are confident enough to use your own words to explain the idea. In contrast, when you read the presentation, that means you don't have confidence or you don't have information about what you are presenting.
Yes.
The second thing, I don't see any figures. So when you want to explain to me something, you need to put at least one figure. So at least you need to add one figure for the circular buffer. So I know that there is head, there is tail. How is the head and tail move when you insert data? So you did not put such thing. The third and most important advice: do not add or try to talk about anything if you don't well understand it. You can give a general idea. If something is like this code, if something is not clear to you, just give an overall idea. Do not try to go to details unless you have like complete understanding of the concept. Actually, I was expecting from you to have at least the general idea, circular buffer. It's good that you made your efforts to prepare the presentation. Thank you, but I expected from you to have better understanding for circular buffer. So I hope by the discussion we made, you had like some insights about the circular buffer, because it's not only used in embedded system. You will see it in other applications, not in embedded system. So I hope that you can read about new data structures and understand them by yourself. So again, thank you, and I hope you my advices was good for you. Okay, so for next session, let us discuss the first step expected from you for the project, and just solve the simple question of drawing the tree from the sequence of the in order, and that's all. Okay.
Okay.
Okay. See you next week.